Hi everybody. In this video we're going to talk about gas laws, and most of what we're going to learn about can be summarized in just one equation. There it is, PV equals nRT. You might be able to guess what some of those variables stand for. We're familiar with N for number of moles and T for temperature. V is for volume here, and R is just a constant called the ideal gas law constant. But we haven't talked a lot about pressure yet, which is what the letter P stands for. Pressure is something we want to introduce now and talk about how it's defined and also what the units of pressure are. We're going to be focusing on gas pressure, and we want to remember that gas pressure is the result of molecular collisions. Just like when a ball hits a wall, it's going to exert a force when lots and lots of gas particles are hitting the surface of a container, then they exert forces on the surface of that container. So while we want to keep in mind that pressure of gas is the result of many molecular collisions that are occurring, the formal definition or the simple definition of pressure is just force divided by unit area. Now there's a demonstration that I've done before which exemplifies well the difference between force and pressure. So if a bed of nails has 200 nails in it and a 200-pound person lies down on that bed of nails, that's only 1 pound per nail, which is not a lot of pressure. It's a large force, but it's spread out over a large area. So when Mr. Anarchist delivers the blow that breaks the cinder block,
5, 4, 3, 2, 1.
the only real danger is that he might miss. So pressure is defined as force per unit area. What would the units of pressure be then? Force in the imperial or British system is measured in pounds, and area can be measured in square inches, and hence we get pounds per square inch, or PSI. But in the metric system, we don't measure force in pounds, nor area in square inches. We measure force in newtons and area in square meters. So the SI or metric system unit for force is the Newton per square meter, which is called a Pascal. More commonly, we're going to be measuring in kilopascals or thousands of pascals. Another common way to think about pressure is to think about atmospheric pressure. Well, an atmosphere of pressure is, of course, the air pressure that we're subjected to every day. Now, it varies a little bit from day to day, but one standard atmosphere is defined relative to many other units of pressure, and we want to be familiar with these different conversion factors. One standard atmosphere is equal to 101.3 kilopascal. It's also equal to 14.7 psi. Finally, we'll talk about a unit called millimeter of mercury, also called the torr, and we want to talk about the historical context of that unit of measurement. So there's many different reasons why we might measure pressure. Of course, you might measure tire pressure in pounds per square inch. You might measure blood pressure with a device called a sphygmomanometer, and we typically use torr or millimeters of mercury there. Of course, we sometimes want to measure what we call barometric pressure, which is measured with a barometer. That is simply another way of talking about atmospheric pressure, and it was developed by Torricelli, who was Galileo's assistant. So let's take a look at this and see if we can imagine how an early barometer or a traditional barometer, a mercury barometer, would work. Perhaps before we talk about a mercury barometer, we'll imagine the same setup with just water. If you filled a test tube with water to the point where it was overflowing, covered it with your finger at the top, and then inverted it into a cup or a trough of water, when you take your finger off, the water would not flow out of the test tube and into the water tub. And that's because in order for that to happen, the water leaving the test tube would have to displace the water in the tub upwards, but atmospheric pressure is pressing down and preventing that from happening. Now, if you had a sufficiently high tube of water, it would have to be over 10 meters tall for this to work, but you would in fact see the water begin to fall away from the top of the tube. That is a measure of atmospheric pressure. Now, with mercury, it's such an incredibly dense liquid that that happens in less than a meter, so only 760 millimeters at standard atmospheric pressure. If atmospheric pressure is a little bit higher, which is what those purple arrows are representing at the bottom, it would prevent the mercury from falling down as much, and you'd have something like 765 millimeters of mercury. But if atmospheric pressure is relatively low, then there would be less force pushing down on that tub, and it would allow the column of mercury to fall. And so that would be a drop in pressure down to maybe 755 millimeters of mercury. When you read the weather forecast, it may tell you inches of mercury, and it's referring essentially to this kind of a device for measuring atmospheric pressure. And that's where the unit millimeters of mercury comes from. The word torr is synonymous with millimeters of mercury and is named after Torricelli, who was a student of Galileo's and is credited with developing the early barometers. Of course, we measure barometric pressure in order to make weather forecasts. You can feel changes in pressure and differences in pressure in your ears. So there's many different examples we can think of as to why measuring pressure is a useful thing to be able to do. Now, we're going to need to convert between different units of pressures pretty regularly. So when we're doing pressure conversions, we're simply going to be using dimensional analysis. See if you can pause the video here and try to remember how to do a simple kind of conversion from atmospheres to PSI, for instance, using the conversion factors that were on the previous slide. Now I'll go back to those conversion factors for just a moment, because these are conversion factors that we're going to want to write down and keep in our notes. We have to refer to them pretty regularly. Let me go back to the questions and see if you can put them to use. So the first calculation is pretty straightforward. We want to go from atmospheres to PSI. We know how many PSI are in one atmosphere, so that's a pretty straightforward dimensional analysis problem. How about the second question, though? The second question is asking to go from PSI to millimeters of mercury, and we don't know how many millimeters of mercury are in one PSI. We can still set up the conversion factor because we know how many PSI are in a certain number of atmospheres. One atmosphere is 760 millimeters of mercury, and one atmosphere is 14.7 psi. So that's a valid conversion factor also. Now, of course, we always want to pay attention to significant figures here. So for the first answer there, I want to round to 3 significant figures, which is the number of significant figures I was given, 40.4 psi. And in the second question, notice I'm going to take 40.50 and I'm going to multiply by 760, and then I'm going to divide by 14.7. And we get 2,093 millimeters of mercury, which makes sense. 40 psi is about 3 atmospheres, and that's about 2,100 millimeters of mercury. I'm going to round that to 4 significant figures. 2,094 millimeters of mercury. Remember, torr and millimeters of mercury are the same thing. So I've got 2 other examples here, and these are just straightforward dimensional analysis problems. So I don't think it's going to be too important to practice these for that reason, but it may be helpful to keep in mind how you could estimate these answers. So for instance, we know that there's 101.3 kilopascal in one atmosphere. So 125.7 kilopascal, that's going to be just over 1 atmosphere. And if you calculated that, you should get about 1.241. Again, rounded to 4 significant figures. In the second question, about how many kilopascal is 810 millimeters of mercury going to be? Well, remember, 760 millimeters of mercury is standard atmospheric pressure, and that's 101.3 kilopascal. So this is going to be over 101. The answer turns out to be 108.0. So while they're simple dimensional analysis problems, it's helpful to be able to ballpark in your mind how many kilopascal per millimeter of mercury or psi, because we're going to be converting between these different pressure units pretty often. So we've talked about pressure, we've talked about how it's defined, and we've talked about the units. Remember that the pressure is only one of the variables we're going to be looking at in an equation that kind of summarizes this unit's content. The volume, the number of moles, and the temperature are other variables that we haven't looked at yet. Let's take a look at temperature briefly and make sure we're familiar with the principles there. Not only how it's defined and what temperature is, but what the units of temperature are. Temperature seems like such a simple idea. I mean, it's just how hot something is, right? We need a little bit more of a sophisticated definition of temperature in this unit. Temperature, remember, is a measure of the average kinetic energy of a sample of matter. Notice some of those particles are moving very fast, and some of those particles are moving very slow. As a matter of fact, even the ones that are moving slowly sometimes get hit by another particle and start moving fast. So that's why we talk about temperature as the average kinetic energy of a sample of matter. It's also important for us to keep in mind that kinetic energy is not simply velocity. Kinetic energy is the energy of motion, and it depends on both velocity and mass. You may remember from a physical science course that kinetic energy in joules can be calculated as 1/2 mv squared, where m is the mass in kilograms and velocity is in meters per second. Now, temperature is directly proportional to kinetic energy, since it's a measure of the average kinetic energy of a sample of matter. Since temperature depends on both mass and velocity of particles, it should make sense that in order for two particles to be at the same temperature, ones that have a higher mass are going to have a lower velocity than those with a small mass, which must have a higher velocity to have the same kinetic energy. Now, there are many ways of measuring temperature. Of course, we measure temperature in Fahrenheit typically, but in the chemistry lab, we're either going to use Celsius or kelvins. In this particular unit, all temperatures must be in kelvins for calculations. There are really no exceptions here. Remember, the way we're going to convert between Celsius and Kelvin is by adding 273. Now you can see here it says the Celsius temperature would be added to 273.15. We will always just add 273 and not keep those last two significant figures. So if you have a 22-degree room temperature, then that would be converted to 295 Kelvin. The last few variables in this formula are nothing new. V for volume and N for moles. However, units matter. Volume will always be measured in liters, and moles, of course, we don't know any other unit for moles other than moles, but make sure your volume is in liters. If you put a volume in milliliters into this equation, you'll get a nonsensical answer. That brings us to the last term, which we haven't discussed yet, R. Now, R is simply a constant. It's an equation fixer. It's a numeric value that only depends on the units that we're using for the other values. Remember that volume is always in liters, N is always in moles, and temperature is always in kelvins. So the only reason the R units will change are if we're using a different unit of pressure. And depending what the unit of pressure we use is, the R value will be different. For now, we're not going to focus on this entire equation, and we're just going to focus on the relationship between pressure and volume. And if the number of moles and temperature are constant, then you can see PV is going to always be equal to the same constant. While I said the entire unit can be summarized in one equation, we're not going to look at this equation in detail until the end of this unit. For now, we're just going to look at pressure and volume. And the relationship between pressure and volume is called Boyle's law. Again, R is a constant. If N and T are held constant, you'll notice this entire equation simplifies into PV is a constant. Now, a constant in a mathematical formula in science is often denoted with the letter K. The ideal gas law constant R is a special one, but usually if we want to pick a letter to denote a generic constant, we're going to use a lowercase letter k. So you may write Boyle's law as just PV equals K. Another more useful way of writing Boyle's law is P1V1 equals P2V2, where 1 and 2 refer to initial and final conditions. Essentially, this is saying that pressure and volume are inversely proportional. As long as the temperature and the number of moles are constant, then the higher the pressure, the lower the volume of the gas. And that should make sense. Boyle's law is spelled B-O-Y-L-E, not B-O-I-L, and it's named after the Earl of Cork, Robert Boyle, who is credited with developing this mathematical relationship. I'm always amused by the title of his publication in the 1600s, which says, "Some motives and incentives to the love of God, pathetically discoursed of in a letter to a friend by the Honorable Robert Boyle." The fourth edition, much corrected. Now, he was an admirer of Galileo, and this was the beginning of a new way of thinking about science. You can see the cover of his publication says, "The Skeptical Chemist, or Chemico-Physical Doubts and Paradoxes, touching the Sphagerous Principles, commonly called hypostatical, as they are wont to be proposed and defined by the generality of alchemists," whereunto is premised part of another discourse relating to the same subject. Now, here we have the beginning of, since he refers to this as the skeptical chemist, some of the principles of scientific method. So by recording results of experiments that anybody could conduct and verify, Boyle was able to establish that there is in fact a simple mathematical relationship between pressure and volume. So what does P1V1 equals P2V2 mean? Well, you can see in this diagram, if the pressure on a gas is decreased from 4 to 2 to 1 atmospheres, then the volume of the gas increases, and the relationship between pressure and volume is inversely proportional. There's two ways we can write that mathematically. PV equals K, or P equals K over V. An even more helpful way is to write P1V1 equals P2V2, where 1 and 2 denote the initial and final conditions. This is an inverse relationship. Most of the relationships we're going to be looking at in this unit are either inverse relationships or they are linear relationships. And this one is inverse. As pressure goes up, volume goes down. Now let's take this equation for a test drive. It says 40 mils of gas is collected at 104.7 kilopascal. Find the volume if the pressure goes to 250. Now before you pause the video to try the calculation, I would consider using the second equation as a way to set up your work. But I would also use your intuition and common sense about this. We are increasing the pressure. What happens if we increase the pressure? Then the volume should decrease. Not only that, but the pressure is more than doubling. So that means the volume should more than halve. See if your calculation verifies that prediction. So here's the shopping list I made. The initial volume is 40 mils. The initial pressure is 104.7. The final pressure is 250. So I'm going to take Boyle's law and rearrange it to solve for V2. I'll plug the numbers in. And you can see that it's true. The volume is more than halved. It looks like 3 significant figures is the least precise measurement I have, so I'll round my final answer to 3 significant figures, 16.8 mils. Let's try one more. See if you can pause the video here and set this problem up. Identify which variables are which, and see if you can solve for the unknown variable the question is asking for. Again, it might be helpful to make a prediction here. If we have half a liter of gas at 75 psi, what volume is it going to occupy as a standard atmospheric pressure? Remember, standard atmospheric pressure, 1 atmosphere, is equal to 14.7 psi. That's a much lower pressure. So at a lower pressure, the gas should expand to fill a much larger volume. Here's the list of variables. The new or final pressure is 14.7 psi. When I plug those numbers in, I get about 2.55, or rounded to two significant figures, 2.6 liters, which makes sense. It's a much larger volume because it's a much lower pressure. Last one. This one is asking you to solve for pressure. See if you can pause the video and get an answer to this question. Again, it's helpful to make an estimate or a prediction here. We're starting with 2 liters of gas at 760 millimeters of mercury. That's 1 atmosphere. And it's going to be compressed down to 1/4 of a liter. That's a huge change in volume, so we're going to need a significantly higher pressure. Here's the solution. The initial conditions are 2 liters and 760 millimeters of mercury. The final condition is only 1/4 of a liter. So we're going to need about 6,100 millimeters of mercury to achieve that low volume. So that wraps up the first section of this unit, where we're just looking at the relationship between pressure and volume, called Boyle's law. The rest of the equation, involving relationships between number of moles and temperature and pressure and volume, will come a little bit later. But each of these relationships are either going to be directly proportional or linear or inversely proportional. Hopefully that was helpful. We'll see you next time.